Hello class, so in this module we are going to go over the 4 different plots that I just spoke about in the last module. The first plot being the radial plot. So here we have the radial plot. Here's our radial plot, and I'm focusing right here. So notice, okay, so here we have the probability density, our chi-square on the y, our distance r from the nucleus here. And again, this is the probability of finding the electron at some distance r here. So y squared versus r. Here at the very highest point, this is the highest probability that's pretty much right on top of the nucleus here. Okay, this is our highest probability of finding our electron close to that nucleus. And notice that here, right at this axis, this is where this point will be 0. Okay, so that starts here where this curve is. That's our highest probability of finding the electron. And as we go further away from the nucleus, our probability of finding the electron decreases. So this should make sense. The electron wants to stay close to the nucleus. Plus likes minus. Okay, so we should see the electron close to that nucleus. So the probability of finding that electron gets smaller and smaller as we get further and further from the nucleus. Okay, so that is our radial plot. Now we're going to go ahead and focus. We're going to focus on the dot plot. So over here, we've got the dot plot. So this is our dot plot. And this little dot in the center represents the nucleus. And what do we notice around our nucleus here? So in this region here, like I drew those dots before, this is the highest probability of the dots here, right in the middle of this sphere, around the nucleus. So that means the probability of finding the electron there is greater. So as we go further out here, as we get further out in this region, we notice the density of dots, they decrease. So finding the electron out here is smaller. Okay, so those are the dot plots. The next type of plot we're going to look at is the radial probability distribution, and that's over here. So the radial probability distribution, that's this plot. So this is the total probability of an electron being in a spherical layer. Okay, so what does that mean? So if we were to take the whole atom and break it up into spherical shells, so like these rings, it's very much like an onion, so layers in an onion. What we see, if we look inside these circles, what we see is the probability of where that electron would be inside those circles. So these circles look, in 2D, they just look like circles, but in 3D, it looks like a shell, just like an onion skin. So we ask ourselves, what is the probability of an electron some distance r, so I'm trying to write on the screen, some distance r located in a shell? Well, what we do for these plots, we take our chi-squared and we calculate it by the volume of the shell. So as we move further and further from the nucleus, notice that the volume of our shells, they increase. So our radius is getting bigger and bigger. We have more space on the outside than in the center. So if we take a look at the center again, right here with the nucleus, that black dot right in the center, we know that the volume in the center is 0. So if we take our chi-square times 0, we get 0, right? So that's why this curve right here, it starts at 0. And what happens is that as we go from the nucleus, what happens is we reach a maximum Okay, so we reach a maximum and it goes up and then to this peak and then it comes back down again. So our typical plots will look like this. They start at 0, so I hope it makes sense why it's 0. The volume where the nucleus is 0 for finding electrons, so it should be 0 there. And we get plots that typically look like this. They'll have a maximum and then come back down. We'll be talking more about these plots, but let me give an analogy. Okay, so here is our analogy. We are going to look at this apple tree. So this is a probability distribution of apples falling from this tree. So we see as the apples fall down, some are going to be close to the trunk. Some of the apples are actually pretty far out here. So some of them roll away. Maybe some critter comes, takes it, and then drops it out here. So what we want to do is get the distance of these apples. So what you do is you mark with rings all around the trunk, and they're going to be equally spaced, and then we're going to count the number of apples in any given ring. Now notice by the trunk there should be no apples. So this is where our volume is 0, just like we talked about the nucleus before. So, and notice here, so that's the 0 for our curve. Right by the trunk there should be no apples. But in your rings that are close to the trunk, the rings are smaller, the volume is smaller, so there might not be as many apples there. So that's why you get a little bit of increase. You have some apples, but not a lot. And then what happens is you move from the smaller rings to the larger rings, you start to get this increase. So our curve increases, and it reaches this maximum. And then what happens is as you get further out, the rings, they get larger. They get larger. And what happens is that it starts to fall off here with the distance from the trunk. So how does this again relate to our radio probability distribution? This area here where I marked before, I'm trying to mark now, this big black line. This is the most probable shell and the most probable distance that you're going to go ahead and find an electron. Okay, so that's a radio probability distribution. Now the last type of plot is called a contour plot, and we're going to go over those more in the next module. But here, or actually just the next slide or next part of the page, here what we want to point out is really with the contour we see the shape. So this is a 1s orbital, and look, it looks like a ball or a sphere. And a lot of you will recall that s orbitals do look like spheres. So we try to get the overall shape when we look at the contour plots. And sometimes the contour plots are just pieces taken out. So there'll be little wedges taken out just so that way we can kind of see what's inside the contour plot. And you'll see that coming up right now. So we looked at the smallest quantum number, the 1s. Let's go ahead and move up to the 2s and 3s. But before we do that, I'm going to point out the different plots again. So here we've got the radial plot. So we've already talked about that. And here we have n equals 1, L equals 0. And if you recall, for the code for 0 just means it's an S. So this is our 1s over here. And here we have our contour plots. Notice the electron density in the center here. It's darker, so that means it's more dense, more likely to find an electron. And here is the probability distribution plot that we just went over for the 1s orbital. Okay. Now let's go ahead and take a look at a 2s. So if we're going to focus on this middle section. So here it would be our wave function. And we would have n equals 2. Our L would still be 0 because S's are 0. And our M sub L would be 0. So the only difference over here was this was a n equals 1 for our 1s. So the way we would write this again for this one would be our psi 2s. So we don't want to write all of those numbers. So shorter notation is our Psi2s. Okay, so this represents a 2 orbital. So let's take a look at our, made that too big. Let's take a look at our radial plot for our 2s. And what do we notice here? We notice that it looks really similar. The radial plot looks similar to the 1s. So it falls off and it goes down, but it reaches this 0 point. Okay, so it goes all the way down to 0. Then it climbs back up again, reaches this peak, and falls down as you move further and further from the nucleus. Okay, so this point here at 0 is called a node. It's actually called a radial node. There is the probability of finding an electron here is 0. Okay, that's what quantum mechanics says. So that's looking at the radial plot. Let's look at the contour plot. So what do we notice about this contour plot? Well, we see that we have a lot of dots in the center. It's pretty dense. It's the darker blue. And what do we have here? So we just talked about that node. Notice the 1s doesn't have a node. The 2s has a node, and it's here in white. It kind of looks like a little heart. Now here, this is the region where there's 0 probability of finding an electron. But what happens is that you start to get out here past that node, and you have a region of space where you can find an electron again. Okay. Now, what happens is as we go further and further, the probability gets larger to find that electron. And notice the shape. The shape is still spherical. So how does this plot differ than the 1s? Well, n increase, the size increases, and we have 1 node. Okay. And if we take a look at our distribution probability, or our probability distribution plot over here, this is going to be, we have 2 points here and here where it's probable to find an electron. Now this is higher, so it's going to be most probable to find that electron here from the nucleus. And then here, this again represents our node. All right. Now, let's go ahead and look at the 3s. So then this would be the wave function for our 3s, its radial plot. So again, we have it falling down, it reaches 0, so here we have a node. And you guys probably see there's another node. So we've got 2 nodes for a 3s, and we've got 1 node for a 2s. Okay. Now, if we look at the contour shape, you can figure, or you can see those nodes again. So here's the first ring in white, there's our first node, and here's the second, there's our second node. And for our probability distribution plot, here is the most probable distance, most likely, where we can most likely find an electron. And one thing that I want to point out is, let me erase this so I can draw a line here. So here at this peak, for the 1s for our plot, here the peak for the 2s, and here the peak for the 3s, this is much like our Bohr orbits. So here it would be like the n equals 1 over here. That's close to the nucleus, and you can see as we get further from the nucleus, these can be represented by the more orbitals moving away. Okay, all right. And one more thing, or more than one thing I want to point out is that here, if I'm looking at these radial plot distributions, I want to point out again that here at 0, so it's 0 at the nucleus, right? So there's 0 volume, so it starts at 0. We have to multiply with psi squared by 0, so we get nothing. It goes up and down, so it goes up here to this little peak, and it goes down, and we have a node. And it gets pretty big out here. And I wanted to talk about that because that represents, again, the shell, when we get further out, has a lot of volume, just like our tree trunk analogy. And one more thing I want to point out, or another thing I'll point out will be in the next module, but it has to do with why you have these 0 nodes here. And we really can't answer that, but I'll describe it in a little bit. I'm running out of time, so I gotta cut this video off.